So, 1968, plus or minus. When I look back on my career, it's amazing to me that I was able to be in the right place at the right time with the right skill set to be able to have the opportunity to work on some of these amazing projects. And we're going to find out today how even more amazing that was because of some of the accidents that happened along the way. It all started out because I took French in high school. My high school French teacher. And when I went to the University of Michigan, they had a foreign language requirement. You had to take 4 terms of foreign language. And since I did well in French, I placed out of 3 terms. So the first term there at Michigan, I signed up for physics with Dr. Jens Zorn. We'll see more of him in a bit. And the first term, I finished my foreign language requirement. And so the second term, I had an empty slot on my schedule while everybody else was taking their second term language. So I looked through the course catalog. Introduction to Computer Programming. That looks interesting. And it was. We did this on an IBM 7090, batch mode things, using our old friend punch card, an actual card from that. And it used a language called Michigan Algorithm Decoder, which was a Fortran-ish language, but much better than Fortran. Locally, produced there. The summer of '67, I went back to Dr. Zorn and said, "Are there any jobs in the physics department that I can, take for the summer?" And he hooked me up with Dr. Thornton Murphy, who was doing an experiment with proton-antiproton collisions. And I got a job scanning and measuring bubble chamber pictures. The idea was we had these devices that were kind of like the size of a bunk bed. They had like 4 of these things, and you took reels of photographs that they had taken of the bubble chamber cycling and put them up on the screen and project them on the screen. And you go through, and the first job of scanning was to go find the frame numbers where interesting things happened. And it was not that skilled a job. There was a bunch of other people there that were not physics majors that were doing it as well as me. But you had to kind of measure the curvature and how many outward going paths there were and so forth. And so we made a list of interesting looking frames. And then I upgraded to measuring, which was going back to the interesting frames and buttons on there to select which, there are like 3 different views of the thing that go through with the little scroll wheels there and put it up on the cursor and push the foot pedal and it'd punch out the coordinates on cards. And you'd kind of go, next picture, and so forth. Ultimately, I upgraded even further. I became the card courier where I took the red wagon full of punch cards several blocks to the computing center every evening to put them through the input window for somebody else to pick up in the morning. And ultimately, I worked up to doing some histogram plotting for them. Since there was a physics student, I could be trusted with that, I guess. The workroom there, you can see it has a 029 punch, key punch, and had one of these Frieden calculators, which is maybe a little obsolete at the time, but it was just fun to watch, multiply numbers and divide numbers. The fun thing about that was that the divide thing, there was a special switch that if you divided by too small a number so it went into a loop, it would stop the thing rather than having to pull out the cord. But to do histogram plotting, what you had to do is take a bunch of cards and sort them in numerical order so you can make the bins. The sorter would only do 1 column at a time, so how are you going to do that for a 3-column thing? Well, Dr. Murphy told me that, showed me first you sort on the low order character, and then you stack them all up and put it through again, and then sort on the middle character and stack them up and put them in and start. So this is a physical representation of what's called a radix sort, I think it is. And so that was a fun thing to learn. Sophomore year, then 2 extra slots in my schedule still, so I took the next computer programming course from Bernie Galler, who was the president of ACM at the time. Still on the 7090, doing batch mode, withing punch cards. But since I had this in with the physics department, I had basically my own personal key punch machine now because I didn't have to go into the workroom with everybody else. I used the one at the Randall Lab. This is almost my first computer graphics. I actually have the fanfold paper from this. But one of the assignments, but I don't really count this because I was just calling out a system routine to plot out solutions to an equation here with December 1967. Second term, sophomore year, I took the next 573 programming course using the new operating system they're working on called Michigan Terminal System, which was beginning to be an interactive system, but I was still doing it in batch mode at the time. The term project was a compiler, but it was all written in 360 assembly language. So I learned how to do 360 assembly language. And there was another course in the catalog in the electrical engineering department, computer engineering, something like that, taught by a guy named Keki Irani. One of the things I noticed when I tried to put this talk together and dug up pictures of people on the lab, on the web of people that I worked with, many of them came from obituaries. And Dr. Irani passed away 6 months ago or 8 months ago, something like that. So, but we'll hear more about him anyway. But he said I couldn't take the engineering course there because I hadn't taken a course in differential equations yet. Why was that important? Because it was a course in analog computers. Anyway, during my sophomore year, I was still working at the Randall Physics Lab, and another professor, Jay Chapman, was trying to upgrade the system. He had a SDS DDP-24, it's kind of the size of a bunk bed, and he's going to make it as a controller for the measuring machine so that you would actually write things onto a 9-track magnetic tape instead of punched on cards. And I wrote some Fortran calibration programs for him and so forth to get that going. But then that summer between sophomore and junior year, 1968, I went over to the Systems Engineering Laboratory, as it was called in the engineering building, which was Dr. Irani's outfit. And I got a job on what's called the CONCOMP project, which was funded by ARPA. It stands for Conversational Uses of Computing. Conversational was University of Michigan's term for interactive. The project was basically to analyze what are called queuing networks. And a queuing network is like the little box there represents a server doing jobs. The circles represent queues or lines waiting in line. So you see a job coming in from the left source, and it took a while to process, and then it went straight into the queue, or else it went down. If the queue was full, it went down and got thrown away, and then the branch coming out of there went 3 different ways depending on probabilities and so forth. So this is a systems engineering sort of thing. And so they had an analysis program that we're working on that would analyze these things. And Vic Wallace was kind of the brains behind that, designing it, another graduate student. The graduate student I worked directly for was Scott Randall. And when I went to him to to apply for the job, he says, "Do you know what a ring is?" And I said, "No, but I can learn." And he said, "Okay, you're hard." So the analysis is going to be on a 360, but actually entering the diagram itself was going to be done interactively on a PDP-9, which we'll go into great detail on shortly. But for the summer anyway, I was just doing batch mode 360 assembly language programming. I was basically a human compiler. They would give me very detailed instructions about this routine has to allocate this memory, put in this, move these pointers around here, add this thing to this ring, take this thing out of that ring. Basically, you can see the ring data structures in there, rings of rings and so forth. So through the summer, I did all of that, in batch mode and got them all plugged together. At the end of the summer, we had a site visit for the funding agency. And we thought what we would do is, rather than show slides on the board, we would make slides on the screen of the interactive terminal. And so I volunteered to help them encode the slides, which is how I got my wedge in the door with Jim Jackson and his computer. I don't actually have any of the actual slides, but they were looking something like the thing on the right there. They were block diagrams of things going in and out and so forth. And so basically the encoding required drawing it on graph paper, counting up the little boxes, converting it to octal, converting it to signed digit octal, and putting bits in and typing those things in and compiling them and so forth. And work, we had a site visit and we showed them what we're planning on doing. So let me talk a little bit about PDP-9. After this, basically, I became Jim Jackson's assistant. And so we worked on this together. So the PDP-9 had, as we advertised in the thing, almost 300,000 cores, divided up into 16K of 18 bits because it was core memory. It had made out of discrete transistors, and actually there's capacitors in there too, so there was a little bit of analog magic going on. We had a Model 33 teletype, and we had a paper tape punch, paper tape, actual paper tape. No disk-based, paper tape was the recording material we had, and we had a 201 data set with a princely speed of 2,000 baud. Now, the interesting thing about the PDP-9 339 system is that it was an asymmetrical multiprocessor, which means the PDP-9 was in there fetching instructions out. It had 18-bit instructions, 4 bits of opcode, 1 bit for indirect, and 13 bits of address. Meanwhile, the 339 processor was also fetching its own instructions out of the thing. It only looked at the lower 12 bits of the word because it was actually designed to be plugged into a PDP-8, which only had 12-bit words, so it was identical to the PDP-8. So, but most of its instructions consisted of move to, draw to, this particular thing. There's a jump instruction, a push jump, and a pop instruction for doing subroutines and so forth. And so both of these things are continually fetching things out. Jim Jackson had put together this beautiful operating system to make this all go. He had cooperative multitasking going, interrupt-driven I/O queues for teletype and paper tape in the 201, a free storage manager, light pen tracking, had a display data structure, which we'll talk about in some more detail later, and he also had written a 2-pass assembler and a screen-based text editor, so you could text edit the thing and then assemble it, all in place. And it was really a great setup. Let me talk about the display data structure. This is an actual diagram out of a thing that I wrote several years later explaining how it works. Again, sometimes I'm going to talk about technologies of the time. This used an enhancement to the line printer called a TN print chain, which had these extra characters to make kind of rough squares and so forth to make diagrams with. But I've kind of enhanced this a little bit, so it's a little more understandable right now. But it was the standard tree structure data structure that we're mostly familiar with. You had the root node. The branch contained possibly a transformation in it, and then node number 1 there draws the whole house. The H on the left is the house outline, and the W is the window, and the D is the door. And so each of those branches could translate its object to the proper location. Node number 1 stood for the whole house. Node number 2 stood for the door with a window in it, and so forth. And what was cool about this was that we didn't just have a data structure with pointers to things and so forth. The data structure itself was the program for the PDP-9. That is, instead of a pointer to the thing, it was a jump instruction to the thing. And instead of a pointer to a sub thing, it was a push jump instruction. So you can see the thread of execution going through here that was basically you set the thing up and you let it go, and the PDP-9 will continually refresh the display like that, which I thought was really cool. But there was a problem with that. Well, here, first of all, here's a branch with an offset. Basically, you push jump to branch number 1, and it did an incremental move where you wanted, called the leaf, an incremental move back again, and then jump to branch number 2, incremental move to where it goes and so forth and back. So instancing basically put the thing represented by the leaf in 2 different places on the screen. But there's a problem with this, a synchronization problem, because these 2 things were fetching things out of instructions most of the time. There were no atomic blocking instructions at the time. People didn't know how to do that yet. So for example, here's the actual OCCL code for the data structure block for a branch. These are all PDP-9, 339 instructions, lower order 12 bits. The 2 yellow things are the offset Y and X and the offset back again. But if the execution happened to be in between those 2, when you updated the data structure, you get a glitch on the screen. But the worst thing was the push jump instruction in the middle and the jump instruction to the next data structure block. That was a 2-word instruction because it needed 16 bits. So the first 3 bits were in the first word where the A is there, and the second word. Now you're screwed if you get this in there. So what Jim Jackson had done is made it so that you could only update the data structure during a frame refresh interrupt. Worked. But it was a little slower because you had a lot of changes to make. They queued it up. So one of the first crazy ideas I did was figure out a way to say, we want to change branch number 2 here. So I save the contents of it, put a display stop instruction in there, and then monitor the pushdown stack to make sure it wasn't in the stack anymore. And when it was out of the stack, then it updated things. Or if it got the instruction counter stumbled across that stop instruction, the interceptor service routine itself, it would do the thing and so forth. It's a little complicated, but it made the thing just really fly. So I think Jim trusted me a little more after that. Anyway, he was working on a program called SELMA, Systems Engineering Laboratory Markov Analyzer. He was the one who did the graphics, the drawing program, in addition to the operating system. And you would create objects and draw things on there. What was interesting about that was it had a gestural interface. That is, the thing in there in the middle, you can see that the non-dotted line is the box representing a server-type object. When you got a light pen hit on that and started up the tracking cross, it would monitor which region you were in the screen, watch that, and down the bottom you could say, if you stroked up and down across it 5 times, that was a delete operation. If instead you just kind of yanked away and started moving it and said, okay, he wants to move it, that's a move operation. And likewise with creating branches on the top left there, you get a light pen hit on the thing there, start drawing down. When you move sideways far enough, it turns a corner and then connect it up that. There were 2 types of branches we had to represent. So the second type of branch is if you get a light pen hit on a line and you did a little kind of circular motion, then it created branch type number 2, and then you could connect it up like that. Pretty cool. Anyway, so we wired the whole thing together using some of my implementation of their algorithm on the 360, and then Jim's thing, and we put these things in there, and the 360 would analyze it. And one of the parts of the program that I wrote, I realized after the fact, was basically a giant sparse matrix multiplication routine for doing Markov things. Anyway, it would print out, we'd send back data, and we'd plot them as graphs of how probability of frequency of how much the queues were full and so forth. Jim Foley was also a graduate student there at the time, and he was kind of a slightly different group than I was in. He was downstairs and so forth, and he was actually working more on systems aspects of computer graphics at the time rather than the rendering aspects. But he asked me to kind of run the program for a while he did some system statistics on it and monitor it and so forth. I generated some data for him to use in his thesis. So that was my introduction to Jim Foley. And there was actually a film made of myself demonstrating this thing that Vic Wallace took to a conference and showed it. And unfortunately, we haven't been able to dig that out. We communicated with Vic, and he has it someplace in his garage or basement and so forth. We're still hoping I'll be able to find it. But anyway, now Jim and I were playing around with the thing, and he had gone to a conference, and he came back. He was really excited, or at least excited as he ever got. He said, I just saw this cool thing. It was a computer that would do 3D things. You could fly stuff around, and I'm pretty sure it was an Adage AGT50, which used analog multipliers to do the matrix multiplication, but it was able to actually rotate things in space. So Jim says, hey, let's see if we can do this in software in the PDP-9. And far thinking, I said, that's not going to work. It's going to be too slow. He said, come on, Jim, let's do it. Okay, so we did it, and ultimately, we got the thing working. Here's a life lesson. Put dates on your pictures if you can. These actually were dated January 1969, but we got some 3D things and rotating around on the screen, and it kind of works for simple objects. And we made a simple model of the Apollo command service module, and made a kind of crude Apollo docking system, and we were actually able to institute backface polygon culling, which wasn't perfect, but helped you understand the thing a lot better. So, 3D graphics. My junior year, I went back and took the W365, but by that time it had turned into a digital computer course, and we used a PDP-8. This is one of the original straight 8s, also known as the brain case, and you can see the modules in there are the same style of modules that we in the PDP-9, but PDP-8 instead. Then one of the other professors there, Don Callahan, had written a program which was basically a batch mode program for analyzing electronic circuits, resistors, capacitors, inductors, and so forth. And you would punch out cards with a particular format to describe the topology and requests for things. And so I thought, hey, we can take Jim's program, modify it to draw electronic circuits instead, and analyze those. And so that became what I call SEL CR circuits. Great name. And so this is that in operation. So you could draw this modified version of the thing to draw electronic circuits, and then it would send them off to the 360, and the 360 would send back data to plot things. And it kind of enhanced a bit for the gestural interface. Like you could now scrub something up and down on something to delete it, or yank away from it, but you also kind of rotate around it to start it rotating in 90-degree increments. Likewise, with a connection line, you could scrub up and down and delete it, or remove away in order to do it. But based on elaborations of his basic thing. My entire career is elaborations of other people's stuff, let me tell you. One of the problems we had in taking the pictures was the 339 was kind of dim. So the first picture we tried to take on this thing, it was washed out. You couldn't see anything. And then we tried putting a piece of black paper over there, which you can kind of see in the outline. And that was kind of ugly. And finally, we wound up taking one picture of me and then turned off the lights and took one picture of the circuit and then used high-quality matting techniques, putting the thing together. These pictures I'm showing because they came out so well. Basically, I was holding a slide camera with one hand and moving the thing up and down and clicking the shutter, and it actually, exposure came out right, and I was amazed. So, a demonstration of the thing in operation. Again, same sort of thing, circuits and the analysis of it. These pictures were dated April 1970, so I've got things so this became my first published paper. The Digital Equipment Corporation User Society Spring Symposium 1970. And it also became CONCOMP Technical Report number 24, blah, blah, blah. One interesting technical aspect about this thing is if you look at the M and the I in this thing, this typewriter had variable spaced fonts. It was an IBM Executive typewriter, it was called, and it would make a wider thing for the M and a narrow thing for the I. Pretty cool. Now, last year I went back to the University of Utah to give a talk, and one of the professors there showed me a copy of this book that recently had come out from the ACM, which was about communities of computing. Chapter 11 of the book was a chapter about computer graphics at Utah, and how ARPA funded it and how that was great things and so forth. But at the end of the chapter, there was this. I'll read you the key parts of it. This was the case with ARPA's efforts at the University of Michigan to fund a major computer graphics project called Conversational Uses of Computers, CONCOMP. At Michigan, the objective was to blah, 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 what I just described. While the CONCOMP program continued until 1970, the University of Michigan did not evolve into an IPTO center of excellence, and as such, its graphics program was not considered a success. It was defunded by the IPTO in 1968. Well, if it wasn't for the CONCOMP project, I would not be in computer graphics. I would be an experimental physicist. So I feel a need to defend the honor of my alma mater. So go blue. Meanwhile, while I was doing this, I became slowly aware of various other labs on the University of Michigan campus. One run by a guy named Bert Herzog, and he had a PDP-8 with a 338 and his own setup there when he was doing CAD on it. The PDP-8 program was PDP-8 was harder to program, so it kind of had a fixed function program in it that the 360 would talk to. People didn't program the PDP-8 other than the system programmer to do that. So it was a different kind of trade-off of things. But I got to know him slowly over time. Also, there's a guy in aerospace engineering called Dr. Richard Phillips, who started using storage tube terminals, which became a thing in those days. Phillips also became active in SIGGRAPH, but I've kind of lost track of him, and I don't know if there's an obituary of him or not. But anyway, also I was in a office with a lot of office mates, all graduate students while I was an undergraduate. And one of my office mates came to me one day and said, I just got this thing in the mail that you might find interesting since you do graphics. It's from the University of Utah. Utah, okay. It was by Gordon Romney, published in 1969. Computer-assisted assembly and rendering of solids. Wow. This is the first time I'd seen it. This is so cool. University of Utah is doing neat stuff. Also, in the appendix, there was some math about homogeneous quarters and so forth. It was my first exposure to that. So I got myself on the mailing list for the University of Utah. They had all these orange books for their things, and so I started my collection of orange books. And I also somehow or other came across a manual for the LDS-1, along with a letter from ENS, which somehow seemed to have gotten the impression that I was going to order ones, which is why they sent me the manual. Anyway, so I followed the University of Utah from a distance for some time. Meanwhile, my senior year, I became a teaching assistant for W365, the PDP-8 programming course. And it was the beginning of my teaching career, which is basically how I put myself through school, through Michigan and Utah. One of the problems with being first lecture I gave, I just rehearsed and rehearsed and rehearsed. And so I went in there and I kind of blurted it out, and I was done in half an hour. And everybody had these glazed expressions on their face, so I had to learn to talk slower. Also, I took the 366 Digital Logic course, which used the same modules, so I learned how to plug those together to make things. Then in the summer of 1970, something interesting happens. All the graduate students finished their theses and left, leaving me alone with the PDP-9. And it became my personal toy for the next 4 years. I actually did one job interview, because I'd graduated myself, bachelor's degree at this time, with, I believe it was Bell Labs, and they were interested in hiring me to work on the command and control system for the anti-ballistic missile system, which didn't seem like a good idea. I wanted to stay at Michigan and play with my toys, so that's what I did. So went into graduate school in the newly formed Engineering School Department of Computer Information and Control Engineering for 2 years. The first year, one of my roommates came back and said, "You got to take this course by this guy who, numerical analysis course. He's just so incredible. He goes in, he just kind of, no notes or anything, he just puts all this great stuff on the board." It was none other than Carl DeBoer, who is also famous in the CAD system, but this is before I knew anything about that, so I just took numerical analysis from him and enjoyed it a lot, but didn't realize what he was doing. And also took 673, the operating systems project, which basically a whole classroom had a group project to build a virtual memory operating system from scratch using what was now called a virtual machine in order to test it. So when I was a graduate student teaching, I became actually the main teacher for CIC365, which is the PDP-8 programming course. And I'm not really sure about this, but I suspect there's a possibility. What I had was everybody learning to program it and also learning interrupts and finding, and had the final course was having a program that was doing something on the teletype while a paper tape punch was copying it, so all interrupt driven. There was another smart young kid there that came through Michigan at about the time, and I believe he might have been in my course. His name was Bill Joy. And so there's a possibility that I taught Bill Joy how to field interrupts. And I also was a TA for the 366 Digital Logic course. There was kind of a funny thing that happened there. We got a whole lot of people signing up for the class from the philosophy department, because to get a degree in philosophy, you had to take a course in logic. And I'm not sure how many of them stuck around long enough. I also taught a course in PDP-9, a PDP-9 projects course of people programming stuff for the PDP-9. And pack rat that I am, I still have the course handouts for most of these courses that I handed out. The interesting thing about this is, notice the purple ink. That was before the days of cheap Xeroxing, and we used what's called the ditto process, which is this purple goo on the thing that would, so seen that. Various other projects I did, got into scientific visualization. First thing I did was inverse square force law, showing planetary orbits. That was interesting, but a little bit boring. What was more fun was using something called the Leonard-Jones potential function, which I learned about in chemistry. And that's the potential is 1 over r to the 12th minus 1 over r to the 6th. You can see a plot of it there. At long distance, it's attractive. At short distance, it's repelling. And it's kind of a rough model of how atoms form molecules. And so just using that as a model, this is all done in fixed point arithmetic. We could not afford the luxury of floating points. So it was a bit of a trick juggling the fixed point to do something like this. But the result looked something like this. This was actually recorded later on. This particular program followed me. I carried it with me to Utah and to JPL because it did such cool things. And the one at Michigan was pretty much like this, except it didn't use as good numerical techniques because I didn't understand them then. So each iteration had better numerical techniques. And also, you could only do a maximum of maybe 10 atoms on the PDP-9, whereas in the later versions of it, you could do more. But you could kind of do fun things and show a lot of, and I use this a lot in the mechanical universe in the programs on thermodynamics to show stuff. The other thing is when I was taking quantum mechanics, I went and programmed some of the functions for particle in a box, infinite square well, that sort of thing. And later on, Zorn and another guy named Pollack actually went and filmed it for me. But you could kind of get the sense of what was going on in superposition of different energy levels, particle in a box. Also, wave packet synthesis. This is using our 3D technology. The horizontal axis is position, and the other perpendicular is the real and complex part of the wave function, and it kind of spirals around the axis and gets bigger and smaller depending on the energy components in the bottom of there. But one of the main interesting one that I did with Dr. Zorn and another student named Mage Gulich was called the spin echo effect. It's followed in 1970. And it was showing what's basically the physics behind what an MRI machine does. And the idea was, we're showing the spin of a proton, that's the solid arrow, when a magnetic field is applied to it. And on the left, you see this is a picture off the screen of what it looked like on the screen. And on the right shows the beginnings of my hate affair with film. This was, we recorded it on a Super 8 film using a sleazy Super 8 camera which didn't have through the lens viewing or couldn't focus on, so everything is kind of out of focus. But this is a compressed version. I'll show you how the spin echo effect works. Basically, the proton spin precesses around the magnetic field vector, and if you make the magnetic field vector rotating itself, then you get kind of a wilder gyration. And you can see that more obviously what's going on if you look in a rotating coordinate system, and it looks something like this. Now, the idea of spin echo effect is that you apply a magnetic pulse to this thing, flip it down 90 degrees, and then a little while later, rotating coordinate system, you apply another pulse twice as long to rotate another 180 degrees. And the way that's interesting is if you're in a non-uniform field, everything's going to precess at a different rate. So everything gets down and starts decohering. Then you give the pulse to flip it over in 180 degrees. And now it's decohered kind of in another direction. And so they catch up with each other. And after a certain amount of time, they're all pointing in the same direction, and you get an echo of the spin. And again, this looks a little bit more easy to see in the top view here in a rotating coordinate system. So pulse to flip it down 90 degrees, and then you wait a little while, and you flip it around another 180 degrees, and then you wait for the decoherence to kind of resume, and eventually the spins are all pointing in the same direction, and you get an echo going on. Now, when we made this film, which is a little longer than I'm showing here, they actually used something called a Technicolor cartridge film projector, which they were able to take these things apart and put their own film in there, and you can see it plugged into the right side to project this thing. There's an easy way to show films in those days. One other thing I did was there was another student who was using this as in a psych experiment for perception of things, and he had actually set up an old stereoscope thing on a stand, and so I was able to do stereo images of this thing, looking through it. You can see the two images, and that looked really cool. It was I always thought line drawings were kind of more magical looking than shaded image graphics because that's not what you normally see in real life, and so. Got the stereo going in. It was one of the things that actually was dancing in front of the screen when it looked cool. some simple attempts at character animation with arm and leg joints, which I didn't pursue too much, but was able to make the thing walk around on the screen and so forth. Now, around 1971, there was a faculty computer graphics seminar that was given that I was not invited to, but all the faculty members were showing off their computer graphics. So I went and was kind of hanging out in the back of the thing in the hallway, and I discovered this kind of long-haired hippie freak out there who had wheeled in a U-matic player and was playing videotapes of his 3D graphics. Oh, and his name was Tom DeFati. And we became friends. I showed him my stuff, and he became the head of SIGGRAPH several years later. Also, at that time, there was a film series by a guy named Jim Loudon, who was kind of an astronomy explainer, in the same vein as like Carl Sagan. And he was showing films that I attended the film show, and it was that was the only way you could see films, no YouTube and so forth, of course. And so he showed films of this place called JPL, where they were doing unmanned. And I thought, wow, that looks like a really cool place to work. But I don't have a degree in astronomy, so what use would they have for me? Okay. So he also showed a film of a guy from Cornell named Carl Sagan, and that's my first experience of knowing who he was. Also in the summer of '71, Bert Herzog gave summer courses to the industry in computer graphics. And he very generously invited me to attend for free the summer course that summer, where I learned about Koons patches from the man himself. Steve Koons was one of his guest teachers. Koons was just a fabulous teacher, and he was just exciting to listen to and so forth. And I got my copy of Koons' Little Red Book out of that. And I actually found this last week for the first time in 40 years. And he described how Koons patches worked and a rendering algorithm for them that used backwards differences. So instead of having to do polynomial evaluation, the entire evaluation consisted of a load, add, store, add, store, add, store. You got a new point out, or a new coordinate of a new point out. This was so cool, exactly the sort of thing that PDP-9 is good for. And so I was able to implement Koons patches rotating on the screen using his backwards difference algorithm. And that was how I started getting going on patches. There are also a few art projects of various art students that I worked on. Back when Jim Jackson was Jim Jackson and I saw a film that was shown of John Whitney's art. And we thought, we can do that sort of stuff on the PDP-9. So we went back and tried writing programs, and it looked like crap. And we realized it takes more to make interesting looking art than what we had. Another student was doing a thing where he needed a 3D thing of a skiing down. There was another thing where there was some dancers, and they wanted a background of polygons doing so forth. The one thing about that was, the paper tape here, which is kind of, you can feed it in two ways to the reader, and if you feed it in backwards, obviously it doesn't work. But there's little arrows on the tape showing which way it goes in. And the artist kept putting the tape in backwards, and they said, look, arrows, see, arrows forward. And nope. So next time you want to load the tape, come to me, I'll load it for you. I'm not sure what the lesson of that is, but anyway, I won't state what the lesson is, actually. Another thing there was an outfit called the Computer Arts Society in England, and the United States version of that, the head of that was at Eastern Michigan University, which was just 10 miles down the road in Ypsilanti. So I got to know him, and they had an art thing going on where people could come in and work on computer art, and they had a chance of either working with Ken Knowlton or me, and everybody except one guy worked for Ken Knowlton, and one guy worked with me, and we spent the week basically making more 3D faces and weird stuff. In 1972, we got a new professor there, Dan Atkins. Actually, I'd already finished my master's degree, but Atkins came out and had this really cool course in computer arithmetic, which I signed up for. The idea was, you could do plug together, NAND gates and do arithmetic with it. And said, oh, funny shapes with lines in between. I know how to do that. And so I wrote a version of the program that this is, a simulated screen, but the primitives, instead of resistors and capacitors and inductors, there was 2 input NAND gates, inverters, and input source and an output sensing lamp. And so did the simulation in the PDP-9 because it's a pretty simple one. So you draw the screen on the screen, hook it up, and then you poke at the top thing and it would turn on. Then you poked at the next thing and it would turn on. And after a 1 second simulated gate delay, that would turn off. Cool. So plug this together and we make a half adder. Now, I was going to make more things and I realized it's going to be a pain doing this over and over and over again. So with some effort, I was able to make it so that the program would define macros. That is, you could say, take this thing and make it a new primitive called a half adder. Now you can create multiple instances of a half adder, and it would do all the internal state properly and so forth. So you could make a full adder with a little more glue logic. Define that as being an adder. String 4 of these together, and then you put like -1 in one input, 0 in the other input, and you kick the carry in, and it would go blink, 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 carry out this other side. So you can see the carry propagation going on here. Now, one of the things that he was teaching about this was how to make this faster. So there was a thing called a carry look-ahead adder, which you could do with 4 adders and then some extra kind of glue logic that would precede what's going on in order to make the thing work. And so define that as a carry look-ahead adder and hook a couple of those together, and you could stick the carry in one side, and it was kind of short-circuited away. If necessary, the carry would come out faster, and so it worked a lot faster. So that was a neat thing. One reminder for myself is, pack rat that I am, I still have the PDP-9 source code for every one of these programs. And one of these days, I might try to write a simulator. December 1972, the Rolling Stone Space War thing came out, and it was so cool. It was talked about this place called Xerox PARC and all the fun things that people were doing there. And so I cold called Alan Kay saying, "This is cool, can I have a job?" And he was polite, but no job was forthcoming. I'm sure he doesn't remember that, random stranger from Michigan. Also, I cold called Robert Sproul. Can I have a job? He was polite, but no job was forthcoming. And it's probably just as well, because if I'd gone to Xerox PARC in 1972, I would never have made it to JPL, which ultimately I preferred. Somebody showed me an interesting trick that could do with PDP-8. PDP-8 created radio noise, basically, when it ran. But if you do an IoT instruction at the proper rate, it interrupted the radio noise so that you could generate static that made tones. And they had written a program that so you could, it would actually play music of a sort on the PDP-8, just kind of on and off. The music that he did was like the Russian national anthem. So there's kind of speculation, why is the computer, arised sons of the, whatever it is. But anyway, also some people in the computing center had done some also similar sorts of things. They would wrap a wire around one of the lights and ran that into an amplifier, and they could do kind of square wave type music. But we had a digital analog converter on the PDP-9. So how can I do better than that? Well, I wrote a program that you could draw a wave shape on the screen and put it in a table, or else you could draw the frequency components and it would synthesize a wave with those frequency components. You could also specify an attack and decay envelope, 4 of these for 4 voices, and also I did kind of half-assed attempt at doing a staff, and I kind of cheated on the treble clef a little bit because it was hard to digitize octal things. So, and that didn't work. I actually had a music compiler that used text that would compile things like that. And so here's a medley of some of the, I went through and got as many different kinds of music as I could find. And my brother also encoded some music. And also I got some stuff from the guy at the computing center who had encoded some stuff. And so here, if it will play. So I did the reverberation by putting all the samples into a ring buffer, and every time I put out a sample, I would shift it right and stick it in the buffer, and add the previous ones. It was like we recorded a history of the last 1,000 samples and shifted right and so forth. And when I showed this to Dr. Zorn, he said, "You are a man of eclectic taste." And I looked that up in the dictionary, and he said, "Yeah, I guess I am." One of the interesting aspects of this was my first gut introduction to aliasing. I knew kind of what was going on, and I actually gave a talk on the thing and had an illustration of this thing, and had this little aliasing. Also, I showed it to somebody in music school, and I didn't expect them to be that enthusiastic about it because it was basically a music box. And the only thing he saw was the crappy treble clef that I had made. It's like he couldn't see anything else. But music, no, treble clef, that's a musical illiteracy. You have to make it look like this, like this. So this is a good life lesson. When you're dealing with artists, you have to speak their language. Now, after I got my master's degree, Dr. Irani called up the director of the computing center, and he was able to get it PDP-9 transferred over as a public resource. It needed to be, the maintenance contract needed to be paid for, and so he was able to get it so that we continue to be paid for that. And he also talked Dr. Bartels, head of the computing center, into paying me to do this, which is so great. So the next 2 years, I was an employee of the computing center with a master's degree. This is about the time the Tektronix 4010 came out, and that's the one that kind of made graphics come to the masses. It was only $4,000, September 1972. We got a couple of them in the computing center. And actually, at one conference I went to, I guess with John Meads, I came back having volunteered to be the secretary of the Tektronix users group, which fortunately for me, it was disbanded by Tektronix before they realized what a flake I was and would never have done anything. Anyway, Tektronix 4010. There was also a device called the Princeton Electronic Products 801. It was like a storage tube, but with selective erase. It would write the picture on a chip, and then had a raster scanner that was scanning it out on a monitor. And then by changing the voltage, you could have erase the trace and draw something else. And so selective erase. Another thing came out with the Adage AGT50, which was kind of like the PDP-9 system, only based on a PDP-11. The only software that came with it is a program called Lunar Lander, which a 2D program that you could fly the lunar module and try to land it. A couple of interesting Easter eggs on that was if you flew in the right place, you discovered there was a McDonald's on the moon. And if you accidentally crashed into the McDonald's, it says, "You have just destroyed the only McDonald's on the moon." That was the only software they had for it. And so I, using the Jim Cell system model, we kind of re-implemented that system on the PDP-11 here. It was a good experience in PDP-11 programming, which came in handy later on. And, but there were all these things popping up around campus that were not, in my department. So I had a scheme. What the University of Michigan really needed was me as the computer graphics guy, computing center, was a device-independent graphics package that would drive all these devices. And since, so I put this together, and since it was return integer tokens, I had to have the first letter. It's a Fortran callback. First letter had to be an I, so it was an integer, and G for graphics. And so I just said, I'm integrated. Okay, let's call it the integrated graphics system. And so all the routines were like that. And over the next 2 or 3 years, I put together this, and it was basically, it had a transformation tree, except it had full matrix transformations in it. And it had a series of callbacks between the device-independent part and the device drivers for each individual thing. So it would call back, and it would be smart enough to make some intelligent decisions on how to update the screen. So I wrote device drivers for all these different things and a few others, as well as the CalComp plotter and line printer, why not? And there's another device, a daisy wheel printer, which I don't know if anybody did this, but the daisy wheel printer had, the tractor was able to go backwards and forwards and left and right, and using the decimal point, you go pixels and trace out things. And so I made a device driver to draw things on it with a daisy wheel printer. So all these different things, if you created a new image or added something, they all did kind of the obvious thing. But the trick is if you change something, if you were on a storage tube terminal and you changed something, it would clear the screen and redraw the new stuff. if you were on the selective erasement thing, it would selectively erase the part that changed and just draw the part that changed. And if a CalComp plotter, it would draw everything. And the 339, 338, and GT40 would update its data structure properly. And it's because the bandwidth was basically the bottleneck. You wanted to minimize the number of characters you had to send it. Now, in the summer of 1973, one of my roommates and I took a vacation trip through the West, visiting all the national parks in the western side of the United States. And we wandered through the University of Utah, and I found my way somehow to the Merrill Engineering Building, and I kind of walked around and said, boy, this is actually a real place. Oh, look, there's a door with Ivan Sutherland's name on it. Cool. So going back, I had this thing, do I want to become Dr. Jim Blinn? I'd never really thought of it before, but it seemed like a good idea. And the advice of some of my friends and a young lady who I wanted to be more than friends with, although she wasn't into it, she said, you're wasting yourself, Jim. You should go to Utah. And maybe she's trying to get rid of me. I don't know. And so I applied to the University of Utah and got accepted. And I found out after the fact that the admissions place at Utah got a call, random guy from Michigan, and they call up Bert Herzog and says, who is this Blinn character? And Herzog said, take him. So Bert got me in. So I finished up the thing in the summer of 1974. I finished the integrated graphic system and attended the first SIGGRAPH conference that summer in 1974. Then got in my car, packed up everything, and went to Disneyland for the first time. And then finally went to the University of Utah and left the integrated graphic system in the hands of Andrew Goodrich, he was also active in SIGGRAPH, but I've lost track of him. And so he wrote up a document on it as one of my first SIGGRAPH papers co-author, along the same time as I did the thing with Martin Newell several years later. So one final life lesson that I want to mention, nothing to do with graphics, but I got in the habit of working nights, and so every time I would go home, I would drive through, and there was a stop sign outside the computing center, and I just sailed, nobody around. Okay, just go through the stop sign. And I'd do this over and over again. And then one day, I was there in the afternoon, drove through the stop sign, and there's a police car there, and he stopped me and got a ticket. Now you might say, oh, damn, I got a ticket. And actually, I was relieved, because I realized that if there was a car in the intersection, I would have plowed right into them. And because we are all have a set of habits and reflexes that basically take over when we're not paying attention. And it's important to keep those things tuned properly. So my final advice to you is always stop at stop signs, even when it's 3 in the morning. Thank you.